The discovery that passing an electric current through water would split it apart was made quite soon after the discovery of current electricity itself. This predates Michael Faraday's work in this area, but it is he who introduced most of the terms that we still use today. Electrolysis was named by Faraday. Though not an exact translation, it means to use electricity to split something apart. Let's remind ourselves of the equipment that we use in electrolysis, almost all of which was named by Faraday. The cell has a positive anode and a negative cathode. The electrodes connected to the cell have the same name and charge. The liquid being electrolyzed is the electrolyte. Pure water is a very poor conductor of electricity, as free ions charged species are needed to carry current in the solution. But water, remember, is a covalent molecule, and at room temperature hardly ionizes, and so the concentration of the ions formed is extremely small. Pure water acts as an insulator at safe voltages. If, however, we add a little sulfuric acid to water, this greatly increases the ability of water to undergo electrolysis without altering the products obtained. If we use electrolysis, we will see bubbles forming around both electrodes, the most around the cathode. If we use a Hofmann voltmeter, we can collect the gases made by each electrode. The gases are made in a ratio of 2:1, but the initial solubility of oxygen in the water sometimes masks this. Testing each gas is the usual way we'll confirm their identity. Let us look closely at what's happening. The ions present in water will be the hydrogen ion and the hydroxide ion. These ions will be attracted towards the electrode with the opposite charge. To use Faraday's own words, I propose to distinguish these bodies by calling those anions which go to the anode and those passing the cathode cations. At the anode, we see oxygen being made. This is a loss of electrons, which go into the anode, and so is an oxidation reaction. At the cathode, we see hydrogen being made. The electrons gained are provided by the cathode. This is a reduction reaction. Combining both reactions that are taking place simultaneously, we get a redox reaction. Notice that the balanced equation gives the gases a 2:1 ratio. Remember oil rig as a way of tracking electrons in a redox reaction. If water is acidified with a hydrochloric acid, the reaction is altered due to the presence of the chloride ions, Cl-. In this case, it's the chloride anions that are oxidized and not the hydroxide ions. So chlorine and not oxygen is made at the anode. The combined reaction is again a redox, with the gases each being made in equal amounts. As chlorine is very much more soluble in water than hydrogen is, it will take a while for the water to become saturated enough to enable any appreciable amount of gas to be seen. And while you're working with it in the lab, remember chlorine is toxic, so take precautions.